Hello there, and welcome to the Sleep Porch. Tonight we're turning our attention to Earth science, the deep story of our planet written in stone, water, air, and time. This is the science of shifting continents and restless oceans, of mountains that rise, erode, and rise again. If this content interests you, please take a moment to like the video and subscribe to the channel. Your support motivates us to continue creating more meaningful videos. Asterisk of invisible forces beneath your feet that shape every landscape you have ever known. Earth science reminds us that the world is not a static place. It is active, layered, and endlessly changing. The ground you walk on carries memories of ancient seas, vanished ice sheets, and volcanic fire. Rivers remember paths they no longer follow. Rocks hold records older than life itself. Even the air above you is part of a system that has transformed again and again across deep time. As you listen, you may find yourself seeing the planet a little differently. Not as scenery, but as a living system in motion, vast, powerful, and surprisingly delicate. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, all you need to do is rest. Let your body soften, and allow your eyes to grow heavy. Let your mind unwind as we explore this fascinating world. Let's begin. Tsunamis can travel across oceans, carrying energy faster than jetliners. In deep water, a tsunami is not a towering wall. It is a long, low swell, with a wavelength so immense that ships may barely notice it moving beneath them. What gives it its power is the enormous volume of water in motion across that vast distance, often triggered by a seafloor earthquake, a landslide, or a volcanic collapse. As the wave nears the coast and the water grows shallower, it slows, and the energy is pushed upward, transforming that subtle swell into a destructive surge. The first sign on land is not always a breaking wave. Sometimes the sea pulls back suddenly, exposing seafloor that is normally hidden. Warnings and evacuation matter because the danger can arrive in multiple waves spaced far apart. This is an ocean-scale transfer of energy aimed toward the coastline. A giant impact likely formed the Moon, reshaping Earth's early history. Early Earth was a crowded place, full of growing worlds colliding as the solar system settled. One leading idea is that a Mars-sized body struck the young planet. The collision would have been unimaginably energetic, launching vaporized rock into orbit. That orbiting debris could then have clumped together, cooled, and become the Moon. If this happened, it did more than create a companion in the sky. It likely reset Earth's surface, stirred the interior, and influenced how the planet cooled. The Moon's presence also affects tides, which shape coastlines and marine mixing. And it helps stabilize Earth's spin axis, reducing extreme wobble over long periods. The most striking part is the intimacy of the relationship. If the Moon formed from Earth's own material mixed with an impactor, then the light above us is connected to the ground beneath us. A single ancient collision may have shaped the rhythm of nights, oceans, and seasons ever since. Continents move a few centimeters each year, and that motion builds mountains. It sounds too small to matter until you imagine it happening every year for millions of years. Modern GPS stations can measure that slow drift, showing entire regions sliding, squeezing, and stretching in real time. When two continents collide, neither wants to sink easily, so rock crumples and thickens like a rug pushed against a wall. That is how the Himalayas grew, and they are still rising as India continues to press north. The pressure does not just lift peaks, it also folds rock layers, drives earthquakes, and redirects rivers. Even after collisions, slow uplift can continue because the thickened crust is buoyant. Mountains are not only built by dramatic moments, they are built by patience, measured in fingernails-sized motions. Rivers can reverse direction when uplift changes the slope of land. A river follows gravity, but the shape of land is not permanent. If a mountain range rises or a region tilts, the downhill gradient can weaken, flatten, or flip. When that happens, water can be captured by a neighboring drainage with a steeper descent. This process can carve new valleys, abandon old channels, and route sediment to an entirely different coastline. Sometimes the evidence is subtle, like a dry valley far too large for the stream inside it. Sometimes it is dramatic, with sharp bends that make little sense unless the river's history changed. River capture shows landscapes behaving like competitive systems, where basins fight for water and erosion redraws borders. A river that seems stable in a photograph can be temporary over deep time, and even its direction can change when tectonics quietly reshapes the slope beneath it. Most of Earth's volcanoes hide underwater, building new crust in darkness. The ocean floor is stitched together by volcanic ridges that circle the planet, where molten rock rises, cools, and becomes basalt. This is how much of the seafloor is born, not in dramatic island eruptions, but along long cracks where plates pull apart. In places, seawater sinks into fresh rock, heats up, and blasts back out through hydrothermal vents. Those vents build tall mineral chimneys, and they can support ecosystems that run on chemistry instead of sunlight. Underwater eruptions can look very different too. Pressure keeps gases dissolved, so lava can ooze into rounded pillow shapes, stacking like dark bubbles. Because the ocean hides this work, it is easy to forget that the planet is constantly resurfacing itself beneath the waves. The map of Earth is being redrawn where almost no one watches. Some volcanoes erupt ice and mud, not lava, and still reshape landscapes. In cold regions and on certain icy moons, cryovolcanoes can release water, slush, or other frozen chemicals that behave like lava in slow motion. On Earth, mud volcanoes are another surprise. They are driven by pressurized fluids and gases pushing through sediments, often where tectonic forces squeeze the ground, or where underground hydrocarbons build pressure. Instead of glowing rivers, you can get fountains of mud, bubbling pools, and sudden flows that bury fields or crack roads. These eruptions can build small cones, create new vents overnight, and release methane and other gases into the air. In some places, they continue for years, quietly piling up layers like an odd kind of geology in fast forward. They remind us that volcanism is not only about molten rock. It is about pressure finding a way out and the surface changing as a result. Volcanic ash can fertilize oceans, briefly feeding massive plankton blooms. Ash is more than dust. It can carry trace nutrients that many parts of the ocean lack, especially forms of iron that plankton need in tiny amounts. When winds spread ash over open water, those particles can dissolve and become food for microscopic life near the surface. If conditions are right, plankton populations can surge, turning patches of ocean greener and boosting the base of the marine food web for a time. This can ripple outward to fish, seabirds, and larger predators that follow the feast. The effect is not guaranteed, and it depends on the ash chemistry, the season, and how the ocean mixes. Still, it is a striking example of how land and sea are connected. A distant eruption can influence life far offshore, not through heat or lava, but through a thin fall of mineral-rich powder that changes what the ocean can grow. Dust from deserts can feed forests, carrying nutrients across oceans. Desert dust can travel astonishing distances, lifted by strong winds into the atmosphere and carried in broad plumes. This dust is not just sand. It includes fine mineral particles that can contain key nutrients such as iron and phosphorus. When the dust settles, it can act like a slow delivery system for ecosystems that are otherwise nutrient-limited. Some of it falls into the ocean, where iron can support microscopic life that forms the base of marine food webs. Some of it falls onto land, where minerals can replenish soils over long periods. The journey can cross entire ocean basins, linking arg regions with distant rainforests and island landscapes. Dust also leaves traces in ice and sediments, which let scientists track changes in wind patterns and dryness through time. What looks like a hazy sky can be part of Earth's nutrient circulation, moving tiny packages of geology into living systems far away. Earth's core is mostly iron, and it helps power the magnetic field. Deep below the mantle, a vast outer layer of liquid metal circulates as the planet cools and as the inner core grows. That moving, electrically conducting fluid generates currents, and those currents produce a magnetic field in a self-sustaining process called a geodamo. Rotation adds order, helping organize flow into patterns that can maintain a global field instead of a chaotic local one. The core is not directly seen, yet its presence is obvious in the way certain seismic waves behave and in the way compasses work. The field is not perfectly steady either. It drifts, changes strength, and develops patches of stronger and weaker magnetism across the globe. Core motion also influences conditions in near-Earth space, shaping the magnetosphere that surrounds the planet. A metal ocean at Earth's center helps make the sky above safer for life. The magnetic field shields us, deflecting many charged solar particles. The sun constantly releases a stream of charged particles called the solar wind, and during eruptions, it can launch far stronger bursts. Without a protective field, many of those particles would slam into the upper atmosphere more directly, increasing atmospheric loss and raising radiation exposure at the surface. Earth's field guides much of that flow around the planet, creating a protective cavity in space and trapping some particles in belts that circled the globe. This shield matters for technology too. Strong solar storms can still disturb it, inducing currents that can disrupt power grids and satellites. But the field reduces the overall impact. Comparisons within our solar system make the point vivid. Mars has only weak, patchy magnetism, and it has lost much of its early atmosphere over time. Earth's magnetic shield is not perfect armor, but it is a powerful filter that has helped the atmosphere remain thick and life-friendly. Auroras are space weather made visible, shaped by Earth's magnetism. When charged particles from space are guided along magnetic field lines toward the poles, they plunge into the upper atmosphere and collide with atoms and molecules. Those impacts excite gases, and as the gases relax, they emit light in specific colors. Oxygen can glow green or red, while nitrogen can contribute blue and purple tones. The result is a shifting curtain that reflects conditions far beyond the clouds. During geomagnetic storms,
Auroras can expand toward lower latitudes, showing that the magnetosphere is being strongly disturbed.
These displays are also tied to invisible currents that flow in the upper atmosphere, part of a complex electrical system linking the Sun and Earth. What looks like beauty overhead is also a diagnostic signal. It tells scientists about particle energy, magnetic connections, and changes in the near-Earth environment. It is a glimpse of our planet interacting with space in real time. Meteorites can include older grains than Earth, formed before the Sun. Some meteorites contain tiny mineral fragments that did not form in our solar system at all. These pre-Olar grains were forged in ancient stars, then blasted into space by stellar winds or supernova explosions. Long before the Sun ignited, those grains drifted through interstellar space, surviving radiation and collisions that could have destroyed more fragile material. When our solar system formed from a collapsing cloud, a small fraction of that ancient dust was swept into the growing disk and trapped inside asteroids. Billions of years later, fragments of those asteroids can fall to Earth as meteorites, carrying stardust into our hands. Scientists identify pre-Olar grains by unusual isotope patterns, which act like unmistakable fingerprints of other stellar environments. A rock that lands in a field can contain material older than our planet, older than our Sun, and older than the idea of a solar system. Impact craters can be hidden by forests, oceans, and erosion. A fresh impact scar can be obvious, a bowl with a raised rim and shattered rock. Give it time, and it starts to vanish. Rain rounds the edges, rivers cut through the rim, and sediments slowly fill the depression. In tropical climates, thick vegetation can hide the shape, and in the oceans, water and sediments can bury it completely. Some craters are so subtle that they were only confirmed after scientists noticed strange rocks, unusual circular patterns, or gravity anomalies that hinted at a buried structure. Drill cores can reveal shocked minerals and melted rock layers that do not form in normal Earth processes. This means Earth has almost certainly been hit more times than our maps show. The surface is not a perfect memory. It is a self-awrying canvas. A crater can exist, do its damage, and then be slowly disguised until it becomes a secret held in stone. Some impacts create shocked minerals, changed instantly by extreme pressure. In a major impact, pressure rises so fast and so high that ordinary rock briefly enters an alien state. Quartz can transform into high-pressure forms that do not occur at the surface, and crystals can develop microscopic features that look like tiny parallel lines known as shock lemony. These changes happen in a heartbeat, without time for slow heating or mountain building. They are forensic evidence because very few Earth processes can create the same signatures. Even when a crater is eroded or buried, shocked minerals can remain, hiding in outcrops or drill cores like quiet proof. Impacts can also create brues, mixtures of broken fragments welded together, and melt sheets that cool into new rock. This is why geologists care so much about shock features. They are a stamp of sudden violence, and they can reveal a collision even when the landscape has long since healed over the wound. The seafloor has trenches deeper than mountains at all. The deepest parts of the ocean are not gentle basins. They are narrow trenches that plunge where one tectonic plate bends and dives beneath another. In some places, the descent is so extreme that the water column above would dwarf the height of many famous peaks. Down there, pressure becomes crushing, and even a small drop in depth is a huge change in force. Yet trenches are not empty. They collect sediments funneled from continents, and they host specialized life that can withstand conditions that would destroy most organisms. Trenches also matter for hazards, because the same subduction zones that create them can generate the largest earthquakes and the most far-reaching tsunamis. They are geological fault lines expressed as landscape long scars in the seafloor, where the planet is actively recycling itself. A trench is a place where the ocean floor folds and the earth swallows a piece of its own skin. The largest volcanic eruptions can cool climate by filling skies with aerosols. When a powerful eruption injects sulfur-rich gases high into the atmosphere, those gases can transform into tiny droplets that reflect sunlight back to space. The result is a temporary dimming of the sun's energy at the surface, which can lower average temperatures for a while. This is different from ash clouds that fall out quickly. These high-altitude aerosols can linger and spread around the globe. The cooling can shift rainfall patterns too, which can stress crops and ecosystems in ways that vary by region. The story of an eruption is not written only near the volcano itself. It can appear in unusual sunsets, in shifted seasons, and in records preserved in tree rings and layers of ice. It is one of the clearest reminders that Earth's climate system responds to sudden geological injections, and that the atmosphere can carry those signals far beyond the original blast. Coal began as plants that were compressed into rock through deep burial. It starts in waterlogged environments where dead vegetation accumulates faster than it can fully decay. That plant matter turns into peat, a dark, spongy layer that can build up over centuries. Later, as sediments stack above it, pressure and heat rise, and the chemistry changes as water and gases are pushed out. The material becomes increasingly rich in carbon, passing through stages that steadily raise its energy content. These seams are more than fuel. They are snapshots of vanished wetlands, where forests and swamps once spread across low basins. Some layers are broken by thin bands of sand or ash traces of floods and eruptions that interrupted the quiet process of accumulation. When miners cut into a seam, plant textures and impressions can appear with surprising clarity, like a pressed memory from a lost world. It is ancient sunlight stored in plants, then sealed and transformed by time. Oil forms from ancient organisms, transformed by heat in buried sediments. In many cases, the starting material is microscopic life from seas and lakes mixed into fine mud where oxygen is limited. As sediments accumulate, the organic matter is buried deeper and temperature rises slowly. Over long spans, complex molecules break down and rearrange into liquid hydrocarbons. The liquid does not always stay where it forms. It can migrate through tiny pores and fractures, moving upward until it meets a sealing layer that blocks further escape. That is how underground traps develop, with oil collecting in rock spaces you would never guess exist. Timing matters. There must be enough organic material, enough burial, and the right temperature window. Too cool, and the transformation stores. Too hot, and the liquid can crack into gas. An oil reservoir is not an underground lake. It is a geological puzzle where chemistry and rock architecture align. Rocks can be older than the oceans and still sit beneath your feet. Ocean crust is constantly recycled at subduction zones, so it rarely survives for very long in geological terms. Continental crust is different. It is lighter, harder to drag down, and it can persist through repeated cycles of collision and rifting. That is why some continental rocks preserve astonishing ages, reaching back into Earth's earliest chapters. The ages are not gases. They come from minerals that trap radioactive elements when they form, then change at predictable rates over immense spans of time. These ancient rocks have lived through continents assembling and breaking apart, through atmospheres changing, and through life evolving from simple microbes to complex ecosystems. Yet, they can still be exposed at the surface, weathering in rain and wind like any other stove. When you stand on an ancient outcrop, you are standing on deep time made solid. Few experiences are so quietly humbling. Earth's atmosphere began with volcanoes, not forests, and it kept changing. Early Earth released gases from its interior through relentless volcanism, building an air that was nothing like what we breathe today. Water vapor, carbon dioxide, nitrogen, and other gases dominated, and oxygen was scarce.
Over long spans, oceans formed as water condensed, and carbon dioxide was pulled down into rocks and ocean chemistry. Later, photosynthetic microbes began releasing oxygen. But the shift was not instant. Oxygen reacted with iron and other materials first, leaving mineral records of a world adjusting to a new ingredient. Eventually, oxygen accumulated enough to transform climate, change the chemistry of the seas, and make more complex life possible. The air above you is not a permanent background. It is a living outcome of geology, chemistry, and biology interacting over deep time. Every breath is part of a planetary experiment that is still unfolding. Plate boundaries are Earth's seams where the planet constantly rewrites itself. At divergent boundaries, plates pull apart and magma rises, creating new crust that spreads outward like fresh fabric. At convergent boundaries, plates collide. One can dive beneath another, forming deep ocean trenches. Powerful earthquakes and chains of volcanoes on land or in island arcs. At transform boundaries, plates slide past each other, locking and releasing in sudden jolts that can shake cities. These seams concentrate change, but they also concentrate surprises. Mineral-rich fluids circulate, building ore deposits. Basins form that can later become fertile plains. Entire coastlines can rise or sink over time. Even the outlines of continents are shaped by where seams form and how they migrate. If Earth had no plate boundaries, it would be a far quieter world. It would also be a world with fewer mountains, fewer recycled nutrients, and a very different surface to live on. Hotspot volcanoes can punch through moving plates, creating island trails. A hotspot is thought to be a long-lived source of heat, rising from deep within the mantle. The plate above it keeps moving, so the volcano does not stay in one place. A new volcano forms over the hotspot. Then the plate carries it away, and another volcano forms behind it. Over time, this creates a line of islands or seamounts that can stretch for thousands of kilometers. A trail is like a wake behind a boat, except the boat is a tectonic plate, and the wake is made of volcanoes. As the older volcanoes move away, they often erode and sink, and coral reefs can build rings that later become atolls. Hotspots help explain why volcanoes can appear far from plate boundaries, and they offer a rare way to measure plate motion using a geologic breadcrumb trail across the ocean. The Hawaiian Islands record plate motion like a slow-moving compass. As you travel along the chain, the islands and underwater seamounts become progressively older because they formed one after another as the plate moved over a hotspot.
This gives Earth scientists a timeline written in lava.
The chain also has a dramatic bend, which hints that the direction of plate motion changed in the past. That bend is not just a curiosity on a map. It is evidence that the surface of the planet can reorganize its movement patterns over immense spans of time. Each volcano also has a life story. It grows from the seafloor. It can build a massive shield, and then it slowly quiets as it drifts away from the heat source. Later, it can collapse in giant landslides that reshape the island's flanks and send debris across the seabed. A string of islands becomes a motion record, and a record becomes a story of how plates travel. Earth is layered like an onion, and the deep interior stays mysterious. We live on a thin crust, but below it, the mantle holds most of the planet's volume, hot enough to flow slowly while still being solid rock. Deeper still, the outer core is liquid metal, and the inner core is solid metal under crushing pressure. We know this without drilling there. We listen to earthquake waves because they bend, speed up, slow down, and sometimes disappear depending on what they pass through. That is how scientists discovered a liquid layer that blocks certain waves completely. Even now, the details are debated. How fast does the inner core rotate? How lumpy is the boundary between core and mantle? Those hidden layers shape volcanoes. Plate motion and the magnetic shield around the planet. Earth's magnetic field flips, leaving stone records of ancient reversals. When lava cools, tiny iron-rich minerals inside it can lock into alignment with the planet's magnetic direction, like microscopic compass needles frozen in place. Over time, those locked directions form a library of past field behavior on the sea floor. This creates a striking pattern. As new crust forms at mid-ocean ridges, it carries the current magnetic signature. Then it moves away, making stripes that mirror each other on both sides. Those stripes help prove seafloor spreading. And they also reveal that reversals are irregular. Sometimes the field stays stable for tens of millions of years. Sometimes it flips more often. A reversal is not like a switch. The field can weaken, tilt, and become complex before it settles again. Life keeps going, but the sky shield changes its shape. The ground can liquefy during earthquakes, turning solid land into flowing sand. This happens in loose, water-soaked sediments, often near rivers, bays, or reclaimed land. Normally, grains press against each other and friction helps them support weight. During shaking, those grains can rearrange and the water between them can take on the pressure. Suddenly, the grains lose their grip and the soil behaves more like a fluid. Buildings can tilt as if the ground became soft. Buried tanks can pop upward like corks. Streets can crack open and spit sandy water in small eruptions called sand boils. Liquefaction is not about the ground melting. It is about the structure of a sediment bed failing for a short, terrifying window. That is why engineers care so much about soil type, drainage, and groundwater depth. The same earthquake can be survivable on bedrock and disastrous on saturated fill. A single grain of sand can reveal a continent's long-vanished mountain range. Sand is not just tiny rock. It is a clue about where it came from and what happened on the journey. Under a microscope, geologists can see whether grains are sharp or rounded, which hints at transport by wind, rivers, or waves. They can also identify minerals and rock fragments that act like fingerprints. Some grains contain zircon, a crystal that can survive intense weathering and still preserve the age of the rock it formed in. By dating zircon from modern rivers, scientists can trace sediment back to ancient sources, even if the original mountains have eroded away to low hills. Beaches, dunes, and river deltas become archives of vanished landscapes. A handful of sand can tell you about uplift, erosion, and long-lost continents rubbing together. It is geology's version of detective work written in grains. Water can carve canyons if glaciers can grind whole valleys in silence. Rivers cut by focusing energy into narrow channels, especially when land is rising or sea level is falling. They can slice downward for ages, leaving steep walls and twisting bends that follow the rock's weaknesses. Glaciers work differently. They are slow-moving masses of ice that drag stones like sandpaper across bedrock. Instead of narrow cuts, they often widen and deepen whole valleys, leaving broad, U-shaped profiles and hanging side valleys perched above. Glaciers can pluck blocks from the ground, then carry that rubble for miles and dump it in ridges called moraines. A river's signature is often sinuous and sharp. A glacier's signature is often wide, polished, and dramatic. Both are powered by gravity, but they reshape the planet on different tempos. One can roar in floods, the other can transform a region while seeming almost still, then vanish and leave its work behind. The crust comes in two types: light continental and dense oceanic. Continental crust is thicker and more buoyant, built from rocks that tend to be rich in silica and lighter elements. Oceanic crust is thinner and denser, and it is mostly basalt, formed from mantle melts. This simple contrast explains much about the planet's shape. Continents rise higher because their crust floats more, like thicker wood on water. Ocean basins sit lower because their crust is denser and sinks deeper. Where the two meet, the boundary can become a dramatic zone of earthquakes, coastal mountains, and steep offshore slopes. Even the chemistry matters for everyday life, because continental rocks weather into many of the soils that nourish forests and farms. The next time you look at a world map, you are really seeing two kinds of crust arranged into one restless surface. Oceanic crust is recycled quickly, so truly ancient seafloor is rare. New seafloor forms, cools, and then begins a slow journey away from its birthplace. As it moves, it collects a blanket of sediment. It cools further and sinks deeper into the ocean basin. Eventually, it can reach a destructive boundary, where it bends downward and disappears into the mantle. Because of that constant conveyor belt, the ocean floor stays geologically young compared with continents. The oldest surviving patches are still only a small fraction of Earth's age. This matters because the seafloor is a moving archive. It records changing ocean chemistry in its sediments, and it carries heat that shapes currents and seafloor ecosystems. It also means the ocean floor is not a permanent stage. It is a temporary skin, always being made, always being removed, like pages torn from a book as fast as they are written. Subduction zones can drag water deep, changing rocks far below. Some of that water is obvious, trapped in ocean sediments and pores. Some is hidden inside minerals that formed on the seafloor, where seed or reacted with hot rock and became part of the crystal structure. When a plate sinks, pressure and heat squeeze and transform those hydrated minerals, and the released water rises into the overlying mantle. That water lowers the melting point of rock, which helps generate magma that can feed volcanic arcs. It also drives strange transformations in the descending plate itself, creating dense, high-pressure minerals that would never form near the surface. This is one reason subduction zones can produce both destructive earthquakes and new crustal material. It is a deep recycling system that uses water as a trigger, carrying a surface ingredient into a place it was never meant to go. Mid-ocean ridges form the longest mountain chain on the planet.
This range is not one famous skyline. It is a stitched line of peaks and valleys that winds through the Atlantic, the Pacific, the Indian Ocean, and beyond. In many places, it rises like a broad submarine plateau, spurred down the middle by a rift where new crust forms. The rocks there are still warm, so the seafloor is elevated. As the crust moves away and cools, it contracts and sinks, which helps shape the deep basins that hold the oceans. Along parts of the ridge, segments are offset by fractures, creating stair-step patterns on the seafloor. The ridge is also a heat engine. It warms seawater that circulates through cracks, and that heat flow influences ocean chemistry over long timescales.
The longest mountain chain on Earth is Rhea, but most of it is hidden under kilometers of water. Caldera collapses can happen after eruptions, leaving vast B-shaped basins. A caldera is not simply a big crater from an explosion. It forms when a large magma reservoir empties enough that the ground above loses support. The surface can then drop, sometimes in stages, creating a broad depression with steep inner walls. These collapses can reshape an entire region in a geologic instant. The new basin can later fill with lakes, grow new domes, or host smaller eruptions that rebuild parts of the floor. Calderas can also create complex landscapes where hot water circulates through fractured rock, feeding geothermal systems. The dramatic shape can persist for very long periods, even as erosion softens the edges. For people who live nearby, the calm beauty of a caldera lake can hide a violent origin story. And the basin itself becomes a reminder of how much empty space can be created underground before the land finally gives way. Basalt is common ocean rock born from magma that cools quickly. The salt is common ocean rock born from magma that cools quickly. It is the dark foundation of the deep seafloor, and it forms in places where the planet's interior can finally release heat. When molten rock meets cold seawater, it chills so fast that crystals stay tiny. That is why basalt can look smooth and fine-grained, even though it began as a glowing liquid. Underwater, the salt often piles into rounded pillows, as if the lava inflated and froze in mid-breath. On land, basalt can spread as wide flood lavas that build step-like plateaus and later weather into rich soils. Basalt is also a traveler. As ocean crust moves away from ridges, seawater circulates through cracks and alters it, adding new minerals and changing its chemistry. In that way, a simple black rock becomes part of Earth's long conversation between ocean and interior. Granite forms slowly underground, growing crystals you can see. It begins as magma that stalls deep in the crust, insulated by rock, so it cools at a patient pace. That slow cooling gives minerals time to grow large, so the final rock becomes a mosaic of interlocking crystals. When sunlight hits a fresh surface, you can often pick out glassy quartz, pale feldspar, and darker specks of mica or hornbold. Granite usually forms far below any volcano, which means it spends much of its life hidden. It only reaches the surface after uplift and erosion peel away the overlying layers, like a sculpture revealed by removal. In places such as Hussite and other great batholith regions, granite becomes towering cliffs because it is strong and fractures in bold patterns. Each visible crystal is a record of time spent cooling in darkness, with the planet taking its time to finish the stone. Obsidian is volcanic glass,
created when lava chills almost instantly. Instead of forming orderly crystals, the melt freezes so fast that atoms are locked in a jumbled arrangement, more like a liquid caught mid-motion. The result can be black, smoky, or even banded, with a shine that looks almost wet in bright light. Obsidian breaks in smooth, curved fractures, producing edges that can be astonishingly sharp. That property made it prized for tools in many cultures, and it still has specialized uses today. Obsidian also carries clues about the eruption that birthed it. Gases can leave tiny bubbles, and subtle chemistry can point to a specific volcanic source. Geologists can trace traded obsidian across long distances by matching its chemical fingerprint, which turns a stone blade into a map of ancient connections. It is fire that cooled too fast to become rock in the usual way, and that is exactly what makes it so remarkable. Pumice is rock full of bubbles, so light it can float. It forms when gas-rich magma erupts and the pressure drops suddenly, allowing dissolved gases to expand like foam. The molten material is stretched into a froth and then freezes before the bubbles can escape. That trapped foam structure makes pumice full of pores, sometimes so many that it feels almost weightless in your hand. After major eruptions, pumice can blanket landscapes in pale layers, and it can also spill into the sea. There, pieces may drift for months, sometimes gathering into large rafts that ride currents across oceans. Those rafts can carry barnacles, algae, and other hitchhikers, offering new stepping stones for life to spread. Over time, pumice becomes waterlogged and sinks, and the floating chapter ends. It is a reminder that even solid rock can behave like a boat if it forms in the right kind of volcanic moment. Metamorphic rocks are rewritten by pressure without fully melting. Imagine rock buried so deep that heat rises, stress squeezes, and minerals become unstable. Instead of turning to liquid, the rock changes in place. Crystals can dissolve and regrow, minerals can transform into new forms, and the whole texture can shift as if the stone is learning a new language. This happens during mountain building, when layers are pushed downward and sideways for long periods. It also happens near intrusions, where heat radiates through surrounding rock like a slow bake. Metamorphism can strengthen rock, or it can create planes of weakness that later guide landslides and erosion. It can turn dull sediments into slate, or alter basalt into dense green rocks packed with new minerals. In some cases, it creates gemstones, which is a beautiful twist in the story. A metamorphic rock is not a different ingredient. It is the same material forced into a new identity by the deep conditions of the planet. Marble began as limestone. Then heat and pressure turned it crystalline. Limestone often forms from shells and chemical deposits in ancient seas. So marble is a transformed memory of ocean life and ocean chemistry. When buried and heated, the original calcite grains recrystallize, and the rock becomes a tight mass of interlocking crystals that can take a high polish. That is why marble can look luminous, almost as if light is slipping a little way into the stone before returning. Impurities add drama. Iron can tint it pink or red. Graphite can make it gray, and other minerals can produce green streaks and swirling patterns. Marble also reacts with weak acids, which is why acid rain can soften carved details over time. That fragility makes it both precious and vulnerable. In a single slab, you can hold a story that begins in a shallow sea, travels through burial and mountain building, and returns to the surface as a stone that humans shape into art. Schist can shimmer because minerals line up under directed stress. Deep underground, pressure can become directional, meaning rock is squeezed more from one side than another. Under that kind of stress,
Platy minerals like mica rotate and grow in a shared orientation, like countless tiny pages stacked in the same direction. When the rock is later exposed and split, those aligned minerals catch the light and flash with a silvery glitter. Schist often forms deep within mountain belts, where rocks have been squeezed, heated, and stretched during tectonic collisions. It can contain garnets that grow like tiny time capsules, and those crystals can reveal the conditions of metamorphism because their chemistry shifts as they develop. Schist is also a storyteller across the landscape. Its layered texture can guide how it fractures, how slopes collapse, and how water moves through cracks. What appears as sparkle is actually a physical record of force, frozen into the alignment of minerals that once flowed and twisted under immense pressure. Gneiss forms banded patterns that look like geology painted in stripes. Those bands are not decorative accidents. They result from minerals separating during intense metamorphism, with lighter minerals gathering into pale layers and darker minerals concentrating into darker ones. The rock may begin as granite or layered sediments, and then be transformed so strongly that its internal components reorganize. Over long periods, heat and pressure can cause partial melting, and that can sharpen the contrast between bands, creating a striking, almost wood grain appearance. Gneiss often appears in ancient cores of continents, places that have survived multiple cycles of collision and rebuilding. When you see gneiss at the surface, you're often looking at deep crust that has been lifted and uncovered, which makes it feel like a window into the planet's interior architecture. The stripes are a map of sorting and deformation, showing how rock can be pushed so far that it becomes both new and deeply familiar at once. Sandstone can preserve ripples, freezing ancient shorelines in stone. A ripple pattern forms in minutes when water or wind pushes grains into repeating ridges. If that surface is quickly buried, it can be protected from being erased and later cemented into rock. Millions of years after the waves are gone, the ripple marks can still remain as crisp as a footprint. Sandstone can also preserve crossbedding, which is a set of slanted layers left by migrating dunes or river bars. Those layers can tell you flow direction, wind direction, and whether the environment was a beach, a desert, or a river channel. Some sandstone beds hold mud cracks too, which point to wet ground that dried in the sun. Together, these features let geologists reconstruct vanished landscapes with surprising confidence. Sandstone is not only a rock, it is a snapshot of motion, preserved by burial and time. What looks like decoration is often a preserved moment when Earth's surface was briefly patented by wind or water. Mud can become shale, then transform again into slate and beyond. It begins in quiet water, where the finest particles settle slowly, building thin layers that can record seasons, storms, and changes in the surrounding land. As more sediment piles on top, pressure squeezes water out and compacts the mud into shale, a rock that often splits into thin sheets along its original bedding. If that shale is later caught in a mountain building zone, pressure can realign its minerals and create slate, which splits along a new direction called cleavage. With more heat and stress, slate can become phyllite, then schist, and eventually gneiss. Each step marking deeper conditions and a stronger transformation. This journey means a simple mud deposit can end up as part of a mountain's core. It is one of the most dramatic upgrades in geology. A soft layer of seafloor mud can become a roof tile, then a glittering metamorphic rock, and later a banded stone that tells of continents colliding.
The rock cycle is not a loop. It is a tangled set of pathways. A rock can begin as molten melt deep underground, then cool into solid stone, then be lifted toward the surface and broken apart by weather. Those fragments might wash into a river, settle into a delta, and harden into layered sedimentary rock.
Later, that same rock might be buried again, squeezed and heated until its minerals reorganize into something metamorphic. It might even melt once more, feeding a volcano that returns it to the surface in a completely new form. The surprising part is that there is no single route. Some rocks never melt. Some never become sediment. Some are altered by hot fluids, changed without dramatic heat or burial. Earth keeps offering detours, shortcuts, and dead ends. The cycle is less like a circle and more like a city map with countless intersections where the planet chooses the next chapter. Minerals grow like recipes, assembling from elements in specific conditions. Think of a mineral as a structure that can only form when the ingredients arrive in the right proportions under the right heat and pressure, with the right amount of water or oxygen present. Change the conditions, and you do not get the same result. You get a different crystal with a different shape, a different hardness, and a different color. This is why the same elements can build completely different minerals depending on the environment. Deep underground, slow cooling can give crystals time to grow large and well-formed. Near the surface, rapid changes can create tiny grains or even freeze a melt into glass with no crystals at all. Some minerals only form where seawater reacts with fresh rock on the seafloor. Others require the squeeze of mountain building. Each mineral is a clue because it can only exist within a narrow window of conditions, like a recipe that fails if the oven is too hot. Quartz is tough, so it survives erosion and fills many beaches. Quartz is a stubborn mineral. Many others break down into clays or dissolve away. But quartz resists both chemical attack and physical wear. Over time, wind and water can grind rock into sand, and the weaker minerals vanish first, leaving quartz behind like a survivor of a long journey. That is why so many beaches glitter with pale, durable grains. Quartz can travel far, bouncing down rivers, tumbling in surf, and still remain recognizable. It can also end up in deserts, where dunes become vast, moving reservoirs of quartz sand. In some places, quartz-rich sands harden into sandstone, which can later be lifted into cliffs and arches. The same mineral can appear in a clear crystal point, in a gritty beach, or in a towering rock wall. Its toughness lets it move through landscapes like a reusable ingredient, reshaped again and again without losing its identity. Feldspar weathers into clay, quietly shaping soils and landscapes. Feldspar is one of the most common mineral families in Earth's crust, and it has a hidden talent. When water and weak acids seep into tiny cracks, feldspar can react and transform into clay minerals. This happens slowly, but the consequences are enormous. Clay helps soil hold water and nutrients, which can support plant growth and influence which ecosystems thrive. Clay also changes how land behaves during rain. It can make slopes slippery, increase landslide risk, and turn paths into sticky mud. In rivers, clay stays suspended for a long time, giving floodwater a cloudy look and carrying fine material far downstream. Over the long spans, clay-rich layers can compact into shale, preserving delicate laminations that speak of calm, ancient waters. This means feldspar does not just fade away. It becomes the foundation of fertile ground, river mud, and whole sedimentary basins. Acquired chemical change becomes a force that shapes the surface we live on. Iron and rocks can rust, staining cliffs red over time. When iron-bearing minerals are exposed to oxygen and water, they can oxidize, forming new compounds that often appear red, brown, or yellow. It is the same basic process that turns old metal reddish, but in rock, it can paint entire landscapes. A gray cliff can develop a warm hue along cracks where water seeps. A fresh landslide scar can look bright at first, then deepen in color as oxidation progresses. In deserts and canyon country, iron oxides can cement sediments into harder layers, helping certain beds resist erosion and stand out as ledges. Iron staining can also reveal hidden patterns in rock, tracing ancient fluid pathways that once moved through the ground. This is why the color of stone is not just decoration. It can be a record of exposure, moisture, and chemical change. Over time, a landscape can shift in color without shifting in shape, as if the planet is slowly repainting the same scene. Some rocks contain tiny zircon crystals, time capsules for ancient ages. Zircon is small, but it is legendary in geology because it can survive almost anything. It forms in hot magmas, then endures erosion, transport, burial, and even metamorphism, often without being destroyed. Inside its crystal structure, zircon can trap trace elements and tiny inclusions, locking away clues about the environment where it first grew. Some zircons found in younger rocks are far older than the rocks that carry them because they were recycled from ancient crust. That makes them like heirlooms, passed from one geological era to another. The oldest known zircons come from the earliest chapters of Earth's history, and they hint at conditions that existed when the planet was still young. Holding a grain that small, you are holding a survivor that has crossed almost unimaginable time. It is a reminder that the smallest objects can carry the longest memories, and the deep past is often preserved in places you would never think to look. Radiometric dating uses natural decay, turning atoms into clocks. Some atoms are unstable. Over time, they change into other atoms at a predictable rate. And that steady transformation can be used like a clock. When a mineral forms, it can trap certain elements while excluding others. As the trapped atoms slowly decay, the balance between parent and daughter atoms shifts in a way that can be measured. Different decay systems work on different timescales, which is why scientists can date events from recent centuries to the earliest Earth history. Volcanic layers can be dated to bracket fossils above and below. Meteorites can reveal the age of the solar system's earliest solids. Even the timing of mountain building can be constrained by minerals that grew during heating and pressure. The beauty is that the clock is built into the matter itself. It does not rely on written records or human memory. It relies on physics that keeps the same pace in the dark, underground, and across deep time. Fossils form rarely, so every preserved shell is a lucky event. Most living things vanish without a trace. Scavengers, bacteria, and weather break bodies down fast, and bones can be scattered before they ever have a chance to be buried. For a fossil to form, the timing has to be almost perfect. Rapid burial helps, especially in mud, ash, or sand that shuts out oxygen and slows decay. Hard parts like shells, teeth, and bones have a better chance, but even they can dissolve or be crushed as sediments compact. Then there is the long wait.
The buried remains must survive heat, pressure, groundwater chemistry, and the slow grinding of tectonics. After all that, the fossil still has to be exposed at the surface, and it has to be noticed by someone who recognizes it. That is why a fossil is more than a simple object. It represents a rare chain of events that succeeded from beginning to end.
Each one is a message that managed to travel through time against long odds. Tracks can fossilize as well, capturing motion from a single day long ago. Bones tell you what an animal was. Tracks can tell you what it was doing. A footprint can preserve speed, direction, and even clues about behavior, such as whether an animal was limping or moving as part of a group. For tracks to endure, the ground must be soft enough to receive an imprint, yet firm enough to hold its shape. Then it needs to be buried quickly, often by a flood or a fresh blanket of sand. In some environments, microbial films help stabilize the surface, preserving delicate details like toe marks or skin textures. Over time, the tracked layer can harden into rock, and erosion may expose it again as a natural walkway from another world. Trackways are especially striking because they preserve a moment, not a body. They are evidence of life in motion. A single slab can show a turning step, a sudden pause, or the parallel paths of animals that travel together across an ancient shoreline. Amber can trap insects, sealing a moment of life in resin. Amber begins as sticky resin oozing from a tree, and resin is designed to protect. It can seal wounds, fend off pests, and harden into a barrier. Sometimes that sticky flow catches a small creature, and the trap becomes an accident of preservation. If the resin is buried and survives long enough, it can transform into amber, a stable material that can last for millions of years. The result is astonishing. You can see delicate wings, tiny hairs, even pollen grains caught in the same flow. This kind of preservation is different from stone fossils. It can capture soft tissues and fragile structures that usually disappear. Amber can also preserve whole scenes, like a snapshot of a forest moment that never moved on. Scientists study these inclusions to learn about ancient ecosystems, climate, and the relationships between species. It is time made visible, held in a warm, colored window. A drop of resin becomes a capsule that carries a living instant into the present. Limestone often began as marine skeletons piled into vast seafloor layers. In warm, shallow seas, countless organisms build hard parts from calcium carbonate. When they die, those fragments settle to the bottom like pale snow. Over long stretches of time, the debris is compressed and cemented into rock, sometimes in layers so thick they become a region's foundation. You can walk across a hillside today and be standing on the remains of ancient reefs and shelled creatures, all packed into stone. These layers also carry clues about oceans long gone. Subtle changes in texture and chemistry can reflect shifting sea levels and changing conditions for life. Later, when this rock is lifted onto land, rainwater can slowly dissolve it, carving caves and sinkholes that reshape the surface in a completely different way. A seabed can return as cliffs, caverns, and whole landscapes. Chalk is made of microscopic plankton shells built grain by grain. It forms from the tiny plates of cocolores, which are single-celled organisms living near the sunlit surface of the sea. Each one makes a miniature armor of calcium carbonate. When billions upon billions die, their remains settle into thick, soft sediments. Over time, that material becomes a rock so fine
it can feel almost powdery. Chalk cliffs can look bright and clean, but their whiteness is really a vast accumulation of microscopic life pressed into stone. Chalk often forms in broad, calm oceans where little mud arrives from land, which lets plankton remains dominate. The scale is what makes it astonishing. A towering cliff can be built from creatures smaller than a dust mote. It is sunlight turned into limestone dust, then stacked into landscapes. Natural gas can be trapped in shells released by tiny fractures. Shale is made of extremely fine particles, packed so tightly that fluids struggle to move through it. Yet it can hold large volumes of gas, both inside microscopic pores and attached to mineral and organic surfaces. The challenge is that the gas is often locked in place, like scent sealed inside a closed jar. To release it, connected pathways must form, and fractures can provide them. Even small cracks can link pore spaces into a network that allows gas to flow. In nature, faults and stress can create these pathways. In some settings, engineered methods do the same, which is why shale gas became an important energy source. The details depend on depth, mineral makeup, and brittleness, because not every shale fractures the same way. The fascination is the scale. A rock that looks dull and solid can store enormous energy in spaces far smaller than a grain of sand, waiting for a route to escape. Salt can flow like putty underground, making domes that trap oil. Deep underground, rock does not always behave like brittle stone. Under pressure and over long periods, it can deform slowly, and salt is especially good at creeping. When thick salt layers are buried, they can begin to rise through denser sediments above, forming rounded structures called domes. As a dome pushes upward, it bends surrounding layers and creates pockets where oil and gas can collect. Salt also seals extremely well, so it can trap fluids for very long periods. That combination made salt domes famous in petroleum geology. But they are fascinating even without drilling. They are moving structures shaped over geological time by gravity and density differences. The idea is wonderfully strange. A mineral you sprinkle on food can behave like a slow liquid at depth, folding the crust into new architecture as it rises. Evaporating seas can leave thick salt layers, preserving ancient climates. When a basin becomes restricted with limited connection to the open ocean, evaporation can outpace incoming water. As water leaves, dissolved minerals concentrate until they begin to precipitate. The sequence is orderly. Carbonates tend to form first, then gypsum, then halite, and in extreme cases, potassium and magnesium salts. These deposits can stack into layers hundreds of meters thick, turning a drying episode into a rock record. Each layer hints at climate and water balance because intense evaporation requires specific conditions. Later, these salts can be buried and preserved, even as the region transforms into something unrecognizable. Evaporide layers also influence modern geology. They can deform, create weak zones for faults, and shape groundwater chemistry. Finding thick salt far inland can be a startling clue that a sea once sat there, shrinking under a dry sky. Some deserts were once seafloors, their dunes hiding marine history. The surface may look like endless sand, but beneath that dryness, there can be layers laid down by waves and tides. Over time, tectonics can lift a region, climate can shift, and water can retreat. What was once seabed becomes land, and later, the land can become desert. Wind then takes over,
reworking older sediments into dunes and spreading sand across surfaces that once lay underwater. In some deserts, marine fossils appear far from any coast, which can feel like a trick played by deep time. Even rock textures can hint at ancient shorelines and reefs preserved beneath younger sand. This matters because it shows how completely Earth can reinvent a place. Ocean, then land, then desert, with each stage leaving evidence for anyone who knows how to read it. A dune field can be the newest layer on top of an older marine signature. The Sahara was once greener with lakes and rivers in recent prehistory. Not in some unimaginably distant era, but within a time that overlaps with human history. Changes in Earth's orbit can shift how sunlight is distributed across seasons, and that can strengthen monsoons, pushing rain farther north than it reaches today. When that happens, grasslands expand, lakes fill, and river networks appear in regions that now seem permanently dry. Evidence comes from ancient shorelines, lake sediments, pollen records, and rock art that shows animals that require reliable water. The idea of a green Sahara changes how you see deserts. They are not always fixed. They can swing between wet and dry phases driven by planetary rhythms. This also helps explain ancient migration routes because people and animals could cross landscapes that would be nearly impossible now. The Sahara is often imagined as timeless, but it has shifted between very different identities. And its sands remember deltas, build new land, but they can sink as sediments compact. A delta looks like fresh territory being added to the map because rivers drop their sediment load as they slow down near the sea. Sand builds bars, mud settles into broad plains, and new channels split and wander. Yet beneath that growth is a quiet problem. Delta sediments are often loose and water-rich, and as more layers pile on, the grains pack tighter and water is squeezed out. The surface can slowly drop even without any rise in sea level. If groundwater, oil, or gas is pumped out, sinking can accelerate because support is removed from below. The result is a landscape that is always negotiating with the ocean. Wetlands can drown, storm surges can reach farther inland, and levees must work harder. A delta is both creation and collapse, and the same river that built it can also help undo it. Meanders migrate sideways, slowly, eating banks and reshaping floodplains. A river bend is not a fixed curve. Water moves faster on the outside of a bend, so it scours the bank and steals material grain by grain. On the inside, the flow slows and sand is dropped to build a point bar. Over years, the bend creeps sideways across the valley, carving new ground on one side, while building new ground on the other. Seen from above, the river can look like it is writing a looping signature across the floodplain. Sometimes, the loops grow so tight that a flood cuts a shortcut, leaving an oxbow lake behind like a discarded ribbon of water. This is not rare. It is one of the most common ways rivers reorganize themselves. If you live near a meandering river, the map is always becoming outdated. The river is not just flowing through the land, it is rearranging the land as it goes. Water can dissolve limestone, creating caves and vast sinkhole landscapes. Rainwater picks up carbon dioxide from air and soil, and that turns it mildly acidic. When that water seeps into limestone, it can slowly dissolve the rock along tiny cracks and bedding planes. Over long spans, small openings widen into tunnels, chambers, and complex underground drainage systems. In places like the Yucatan Peninsula, networks of flooded passages connect openings that look like quiet pools from above. At the surface,
Sinkholes can form when roofs thin and collapse, sometimes suddenly enough to swallow roads or buildings. In other areas, the ground becomes pocked with depressions, springs, and disappearing streams because water is rooted underground instead of staying on the surface. This kind of terrain can be beautiful and hazardous at the same time. It also acts like a hidden plumbing system, moving water quickly and making pollution spread faster than people expect.
Stalactites grow from dripping chemistry, not from flowing streams. A cave drip may look small, but it can build stone slowly, one chemical moment at a time. As water percolates through limestone above, it dissolves a little calcium carbonate. When the drop reaches open cave air, carbon dioxide escapes from the water, and that change forces some of the dissolved material to precipitate. A tiny ring of calcite is left behind on the ceiling, then another, and a hollow tube can start to form. If the droop stays steady, the tube thickens into a cone that lengthens downward. On the cave floor, matching deposits can grow upward where drops land, and over long time spans, the two can meet. Color bands can appear from trace minerals which turn the growth into a record of changing water chemistry and soil conditions above. These formations feel timeless, yet they are built by the simple physics of a drip letting go of gas. Cast terrains can swallow rivers, sending them underground for miles. In cast regions, a river can arrive at a crack, widen it over time, and then vanish from the surface entirely. The water does not stop. It simply takes a new route through tunnels and fractures, sometimes reappearing as a spring far away. This can create landscapes where valleys seem strangely dry, even in wet climates, because the drainage has been stolen underground. It can also produce rivers that behave in unexpected ways, rising and falling quickly after storms, since the subterranean pathways can carry water fast. In some karst areas, caves become the main highways of flow, connecting sinkholes, sinking streams, and distant springs into one system. That hidden network makes water resources both precious and fragile. A spill can travel without much filtering because the water bypasses soil and moves straight through rock conduits. Karst is a reminder that a river is not always a visible ribbon. Sometimes it is a journey in darkness. Some caves hold ancient air sealed away for thousands of years. A cave can act like a natural vault. If passages have limited airflow and are protected from frequent flooding, pockets of air can become isolated from the outside world. Over time, that trapped air can preserve chemical signatures from the past, including levels of greenhouse gases, dust, and even traces of ancient wildfires carried as microscopic particles. Cave sediments and crystals can also lock in clues about rainfall and surface vegetation, because the water feeding a cave carries a fingerprint of the ecosystem above. In some places, ice within caves preserves frozen layers formed during colder periods, and those layers can hold their own trapped gases. What makes this so fascinating is that caves are not just empty spaces. They are slow recorders, quietly storing information with fewer disturbances than open-air environments. Entering a cave can feel like stepping into stillness. But for scientists, it can feel like stepping into a preserved sample of an earlier atmosphere. Glaciers store past atmospheres as bubbles trapped in ice. When snow first falls, it is fluffy and full of spaces. As more snow piles up, its weight compresses the layers below, and the snow turns into firn, which is dense but still porous. Eventually, the pores close off, and tiny pockets of air become sealed as bubbles inside solid ice. Those bubbles are not just empty, They are samples of ancient atmosphere captured at the moment the pores closed. By extracting and analyzing the gases, scientists can measure past carbon dioxide and methane levels and compare them with temperature records from the ice itself. That makes glaciers and ice sheets a paired archive of climate and air. The remarkable part is the fidelity. The air in a bubble can be tens of thousands of years old, yet it can still be measured with precision. A glacier is not only frozen water, it is a library of breath from earlier worlds. Ice cores record climates year by year, like layered diaries. In places where snow accumulates without melting, each year can leave a distinct layer. Some layers are lighter or darker, depending on seasonal changes in snowfall, dust, and chemistry. Over time, those layers stack up, and a drilled core becomes a vertical timeline you can hold. Scientists can read volcanic eruptions as ash and sulfate spikes because distant basts leave traces that settle onto the ice. They can also track shifts in wind patterns through changes in dust and shifts in ocean influence through sea salt markers. Even temperature can be inferred from the chemistry of the water molecules themselves, because isotopes vary with cold and warmth. The beauty of an ice core is its steadiness. It does not rely on stories passed down. It relies on snowfall arriving, freezing, and staying put. When a core is laid out, it is like a timeline of winters and summers stacked in order, waiting to be interpreted. Glaciers can surge suddenly, racing forward far faster than usual. Most glaciers move slowly, often at rates that feel almost motionless. A surge is different. Some glaciers spend years building internal stress, then suddenly accelerate, speeding up by an order of magnitude or more. The causes can vary. Meltwater can lubricate the base, reducing friction. Internal deformation can reorganize flow. In some cases, subglacial sediments can act like a weak, slippery layer that suddenly allows the ice above to slide. During a surge, the glacier can thicken in places, crack open into chaotic creases, and bulldoze debris forward. Downstream, river channels can be blocked, and lakes can form behind ice dams. The strange part is the rhythm. A glacier can behave calmly for decades, then enter a brief period of dramatic motion, then settle again. It is like a slow machine that occasionally lurches. Surges remind us that ice is not only a passive remnant of cold. It can be an active force that changes landscapes on human timescales. Moraines mark glacier edges, leaving ridges of rubble as signatures. A glacier is not clean ice. It picks up rock fragments from valley walls and from the bed beneath it, then carries that debris like a moving conveyor belt. When the ice margin pauses or retreats, the debris can be dropped in place, building ridges that trace where the glacier once stood. These ridges can be sharp and fresh-looking, or softened by time and vegetation. But either way, they are signatures of past ice positions. Terminal moraines can mark a glacier's farthest advance, while lateral moraines can run like rails along the sides of old valleys. In many regions, moraines also act like natural dams, holding back lakes that did not exist before the ice arrived. Hikers often walk along moraine crests without realizing they are walking on a former glacier boundary outlined in stones. A moraine is a landscape drawing made by ice, using rock as its ink. The last ice age reshaped coastlines, and sea level rose afterward. When ice sheets spread across continents, they locked up so much water that global sea level dropped dramatically. Shorelines shifted outward, and places that are shallow seas today became wide coastal plains. People and animals could cross regions that are now underwater, and river systems carved valleys across exposed shelves. As the climate warmed, melting ice returned water to the ocean, and coastlines moved inland again. That rise drowned river valleys, created new bays, and rewrote the edges of continents. It also flooded low areas where sediments had collected for thousands of years, turning former land into seabed. Modern coastlines are not ancient boundaries. They are a recent snapshot shaped by ice, meltwater, and time. When you stand at a beach, you are standing on a moving line that has wandered back and forth across the map, guided by the planet's changing storage of ice. Isostic rebound lifts land after ice melts, slowly changing shorelines. A heavy ice sheet presses the crust downward, not because the crust is weak, but because the mantle beneath can flow over long time spans. When the ice melts away, that weight is removed, and the land begins to rise again. The rebound is slow, measured in millimeters each year, but it can continue for thousands of years after the ice is gone. This uplift changes local sea level, even if the ocean itself stays the same. In some regions, former beaches now sit high above the water as raised shorelines and terraces. Harbors can become shallower, wetlands can shift position, and the apparent shape of a coastline can change without any tectonic collision. The landscape is still recovering from an ancient burden. It is a reminder that ice does not only carve and deposit, it can also bend a planet, and a planet can spend ages springing back. Fjords are drowned glacial valleys carved deep, then flooded by seas. A fjord begins as a glacier's workshop. Ice flows through a valley and grinds the bedrock, deepening and widening it while plucking blocks from the walls. Because ice can erode below sea level, the valley floor can become extraordinarily deep, often deeper than the nearby ocean. When the glacier retreats and the sea moves in, water floods the carved basin and creates a long, steep-sided inlet. Many fjords also have a shallow sill near the mouth, built from debris or shaped by erosion patterns. That sill can affect circulation, trapping deeper water and influencing marine ecosystems. The result is a landscape that feels almost unreal, with towering walls rising straight from dark water. Fjords are not just scenic, they are evidence that ice can sculpt rock on a grand scale. Then, hand the finished basin to the ocean. Loess is wind-blown silt, making fertile soils far from its source. Loess looks like simple dust, but it can build thick blankets of silt across entire regions. It often forms when glaciers grind rock into fine particles, and rivers spread that sediment onto plains that dry out seasonally. Wind then lifts the silt and carries it away, sometimes hundreds of kilometers, before it settles in layers. Loess deposits can stand in steep, almost vertical faces because the grains interlock in a way that gives surprising strength. Over time, loess can weather into soils that are rich and productive, which is why many major farming regions sit on loess's plains. The fertility is not magic. It comes from mineral content, good water retention, and a structure that roots can penetrate easily. Loess is a reminder that landscapes can be linked by airborne pathways. A glacier can help feed distant fields, not by rivers alone, but by wind. Weathering breaks rock chemically, while erosion moves it physically. A cliff can crumble because two different forces are working together. Weathering changes rock in place. Water can dissolve minerals. Oxygen can transform iron into oxides, and acids from soil can alter crystals into clays. These chemical shifts weaken the material and change its texture, often from the inside outward. Erosion is what carries the loosened material away. Flowing water, wind, ice, and gravity transport fragments downstream, downslope, or downwind. The difference matters because a landscape can be heavily weathered yet not eroded much if the broken material stays put. Or it can be strongly eroded with little chemical change if physical removal is dominant. Together, they create the supply chain of sediment that builds beaches, deltas, and seafloor layers. They also shape scenery in different ways. Weathering can round boulders and soften edges. Erosion can cut sharp valleys and reveal fresh surfaces. One prepares, the other delivers. Freeze-thaw cycles can shatter stone, prying cracks wider each winter. Water seeps into a tiny crack, and that does not seem dramatic. Then the temperature drops and the water freezes. Ice expands and the pressure can push the crack slightly wider. When thaw arrives, more water can enter the enlarged space, and the next freeze repeats the process. Over many cycles, solid rock can fracture into blocks and fragments, especially in climates where temperatures cross freezing often. This process can create piles of angular rubble at the base of cliffs, and it can weaken slopes until rockfalls occur. It also helps produce the raw material for soil and sediment, turning bedrock into smaller pieces that can later be moved by streams or wind. Freeze-thaw weathering is a slow lever applied again and again, and it can be more effective than a single dramatic storm. It is one reason mountains in cold regions can look jagged and freshly broken. The chisel is not a tool, it is water changing state. Roots can split rock, turning biology into a slow geological force. A seed can land in a crack, sprout, and send roots into spaces that were once too small to notice. As the root grows thicker, it exerts pressure on the crack walls. The force is steady, and it can widen fractures over time, especially when combined with moisture changes that make roots swell and shrink. This is not just damage, it is a pathway for soil formation. Once cracks widen, more water enters, more minerals weather, and more organic material accumulates. In some landscapes, plant roots help stabilize slopes by binding loose material. In others, they help dismantle cliffs by prying blocks apart. Lichens and microbes add their own influence by producing acids that alter rock surfaces, preparing them for physical breakage. The result is that living things do not simply occupy geology. They participate in shaping it. A forested hillside is not only covered by life, it is being worked on by life, one root at a time. Soil is alive, built by minerals, microbes, water, and time. Soil is not just crushed rock. It is a layered habitat where minerals mix with decaying organic matter, air, water, and living communities. Weathered rock provides the base particles, but biology gives soil its behavior. Microbes break down dead material, release nutrients, and build compounds that help bind grains into stable crumbs. Fungi extend networks that move water and nutrients through the ground, and plant roots pump sugars into the soil to feed the organisms that support them. Soil structure matters as much as chemistry. Good structure allows water to infiltrate, prevents erosion, and lets roots breathe. In a healthy system, Soil can store carbon, filter pollutants, and buffer floods by absorbing rainfall. It also records history because layers can preserve traces of past vegetation, fire, and land use. When soil is lost, it is not easily replaced because its formation depends on slow interactions between rock, climate, and life. It is a living skin that makes terrestrial ecosystems possible. A single teaspoon of healthy soil can hold billions of microbes. That small scoop can contain bacteria, fungi, archaea, and microscopic predators, all interacting in a dense underground community. These organisms decompose leaves, recycle nutrients, and help make minerals available to plants. Some microbes fix nitrogen from the air into forms roots can use. Others produce natural antibiotics that influence which species thrive.
In the space around a root, called the rhyosphere, microbes respond to sugars and signals released by plants, and in return, they can help defend roots from disease or improve access to phosphorus and other nutrients. This hidden world also shapes climate, because microbes regulate how quickly carbon is released from decaying material or locked into more stable forms. The diversity can be astonishing. Two nearby patches of soil can host very different microbial communities, shaped by moisture, plant types, and past conditions. When you hold soil, you are not holding mere dirt. You are holding an ecosystem operating beneath your feet, carrying out chemistry at living speed. Earthquakes can set off landslides, reshaping valleys in minutes. When shaking rattles a slope, gravity suddenly gains the upper hand, and rock that was stable yesterday can turn into a moving mass. Some slides are shallow and fast, sweeping away soil and trees like a rough broom. Others are deep failures that slump in massive blocks, leaving fresh scarps and tilted ground behind. The most dramatic can dam rivers, forming temporary lakes that may later burst and send floods downstream with little warning. In mountain regions, quake-triggered rockfalls can rain into valleys, burying roads and shifting river channels in a single event. Even after the dust settles, fractured hillsides can remain unstable for years. A later storm can remobilize loosened debris into destructive flows. An earthquake is not only shaking, it can also be a sudden rewrite of slopes, rivers, and the shape of a landscape. Some faults creep quietly, sliding without big quakes for years. Instead of locking tightly and releasing in one violent snap, parts of certain faults move a little at a time. The motion can be slow enough to measure with GPS, or by watching a painted line across pavement drift out of alignment. This kind of steady slip can bend rails, crack walls, and gradually deform the ground. Yet it may not produce the sharp shaking people associate with earthquakes. Creep can happen when rocks along the fault contain minerals that slide more easily, or when fluids reduce friction at depth. It matters for hazard planning because a creeping segment may relieve stress locally while transferring stress toward locked segments nearby. It also gives scientists a rare chance to study a fault while it is moving, not just after a disaster. A fault that creeps is still active. It is simply choosing a quieter way to move. Liquefaction can tilt buildings even when the structure stays intact. During strong shaking, saturated ground can lose its strength and behave more like a fluid than a solid foundation. A building may not crack in half or collapse, yet it can begin to settle unevenly as the ground shifts beneath it. One corner sinks, another lifts slightly, and the whole structure leans, as if it were gently pushed.
Roads can buckle, buried pipes can float upward, and bridges can lose support at their approaches. This is especially common in young river sediments, coastal fills, and reclaimed land where the grains are loose and groundwater is close to the surface. Afterward, the damage can be deceptive. Walls may look fine, but doors no longer close and floors slope. Engineers reduce risk by densifying soils, lowering groundwater, or transferring loads to deeper, stable layers with piles. The unsettling lesson is that a building can survive the shaking, yet still be displaced by the ground itself. Seismic waves reveal Earth's interior, like ultrasound for a planet. When an earthquake happens, it sends vibrations through the planet that travel at different speeds depending on what they pass through. Some waves move through solids and liquids, while others cannot travel through liquids at all. By recording arrival times at many stations, scientists can map changes in velocity that point to hot regions, cold slabs sinking into the mantle, and boundaries between major layers. This is how the size of the core was inferred, and how its liquid outer layer was confirmed. Modern seismic imaging can even show remnants of old plates deep below, like fossils of vanished oceans. The data also reveal unexpected features, such as zones where rock is partially molten, and regions where the mantle structure looks unusually complex. The remarkable thing is that the planet is constantly being scanned, without drilling. Every earthquake becomes a signal source, and every seismometer becomes an ear pressed to the ground. The mantle convects slowly, driving plate motion with deep heat. Rock there is mostly solid, yet over long spans it can flow because pressure and temperature allow minerals to deform. Heat from Earth's interior makes some regions rise, while cooler, denser material sinks, creating circulation on a planetary scale. This circulation helps pull plates apart at ridges and draw them down at subduction zones, linking deep processes to surface geography. In some places, the sinking of a cold slab can act like a heavy curtain, tugging the rest of the plate behind it. In others, upwelling mantle can thin the crust and encourage rifting. The speeds are small in a human lifetime, but the consequences are enormous over millions of years. Continents move, oceans open, and mountain belts rise because the mantle keeps transporting heat upward. It is Earth's slow engine, turning deep warmth into surface change. Tektites are natural glass formed when impacts melt and fling rock. When an impact is large enough, it can melt surface rock and launch droplets high into the atmosphere. Those droplets spin, cool, and harden into glassy objects called tektites. They can land far from the crater, sometimes scattered across huge regions, known as strewn fields. Tektites often have aerodynamic shapes because they were still soft while flying through air. Their surfaces can be etched and pitted, shaped by heating and ablation during the trip. Unlike volcanic glass, tektites usually show very low water content, which reflects their violent formation and rapid cooling. Finding them can feel like finding messages thrown across continents by a single ancient event. They link far-flung landscapes to a shared moment of impact. A small, dark pebble can be a traveler from a catastrophe formed in fire, launched into the sky, and dropped back to Earth as a cooled fragment of a split second. Deep time is measured in eons, far beyond everyday imagination. Human life is measured in decades, and history in centuries. Earth's story is measured in spans so large that the mind resists them. An eon is not a long time.
it is a category for long time. Within eons are eras, periods, and epochs, each marked by major shifts in climate, oceans, and life. These boundaries are not chosen for drama. They are chosen because rocks change character across them. Chemistry shifts, fossils appear or vanish, and sediments tell a different environmental story. Deep time also reshapes how you see the present. Mountains are temporary. Coastlines are recent. Whole oceans can open and close. What feels permanent is often just the current frame in an immense film. Geology gives us a way to read that film using layers, minerals, and isotopes as timestamps. Once you start thinking in eons, the planet stops being a backdrop. It becomes a long-running process that you have entered mid-chapter.
Mass extinctions reset ecosystems, and geology preserves their clues. Life can be resilient, but it can also be knocked back hard enough that the world reorganizes. In a mass extinction, many species disappear in a geologically short interval, and the survivors inherit a changed planet. Forests can shift, oceans can reorganize, and food webs can be rebuilt from the bottom up. The clues are not only in fossils, they are also in rock chemistry, in sudden changes in carbon isotopes, in layers rich with ash, or in black shells that hint at low oxygen seas. Sometimes there are signs of widespread wildfire. Sometimes there are hints of rapid warming or acidification. Afterward, the rock record often shows a new kind of ecosystem taking hold, with different dominant groups and new strategies for survival. These events can be tragic, but they are also creative in a cold way. They open ecological space and accelerate evolutionary experiments. Geology keeps the receipts layer by layer, showing how catastrophe can become a turning point.
The Permian extinction left chemical scars in rocks worldwide. The end Permian event was the largest known mass extinction, and it left a global fingerprint that goes beyond missing fossils. In many places, rocks from that boundary show sharp shifts in carbon chemistry, suggesting a major disruption to the carbon cycle. Some layers indicate widespread oxygen loss in the oceans, which would have stressed marine life, even in places far from shore. On land, ecosystems also collapsed, with forests thinning and food chains breaking. One leading suspect is massive volcanism in what is now Siberia, which could have released enormous amounts of gases that drove warming, acid rain, and ocean changes. The details are still debated, but the geological evidence points to a planet pushed hard and fast.
The aftermath looks like a slow recovery, with simpler ecosystems persisting for a long time before diversity returned. What makes it haunting is the scale. It was not a local disaster. It was a whole Earth crisis, written into rocks on multiple continents. Ocean anoxia can spread, suffocating marine life and altering sediments. The ocean is not always well mixed. In certain climates and circulation patterns, deep waters can lose oxygen faster than it can be replaced. When oxygen levels fall, normal decay processes change, and organic matter can accumulate in dark, carbon-rich muds. These conditions can be deadly for many animals, especially those that cannot escape to shallower, oxygenated water. Anoxic events can expand across basins, sometimes leaving widespread layers of black shale as evidence. Chemistry shift too. Elements that behave one way in oxygenated water behave differently without oxygen. So sediments record a clear change in how the ocean was functioning. These events are more than a marine tragedy. They can influence carbon storage, nutrient cycling, and long-term climate.
They also remind us that ocean health depends on circulation, not just on life itself. The sea can look calm at the surface, while deep waters become hostile, reshaping ecosystems from below. Reef limestone can record sea level changes like a stone tide gauge. Coral reefs grow near the surface where sunlight reaches, and that makes them sensitive to sea level. If sea level rises slowly, reefs can build upward and keep pace. If it rises too fast or falls too far, the reef can drown or be exposed, and growth patterns change. Over long spans, these shifts can be preserved in reef limestone as stacked layers, terraces, and repeated growth surfaces. Some reefs even form step-like features that mark pauses or reversals, like notches on a ruler.
Because reefs are widespread and can be dated, they help scientists compare sea level changes across regions and time. Reef limestone can also preserve storm deposits and evidence of ancient wave energy, adding more detail to the story of shifting coasts. A reef is not only habitat, it is architecture, built to match the waterline. When that waterline moves, the reef responds, and the rock record remembers. Coral fossils can reveal ancient ocean temperatures through their chemistry. Corals build skeletons from calcium carbonate, and as they grow, they incorporate tiny variations in chemical ratios that depend on water conditions. Those variations can act like a thermometer. By measuring certain isotopes and trace elements in fossil coral, scientists can estimate the temperature of the water when that coral was alive. Corals can also show seasonal bands, a bit like growth rings, which can preserve patterns of warming and cooling across a year. This is powerful because it provides direct evidence of past ocean conditions, not just indirect hints. Fossil corals can help reconstruct ancient currents, past climate swings, and the history of warm periods and cool periods. They also reveal how sensitive reefs have been to environmental change, which matters for understanding their future. A coral fossil is not just a pretty pattern in stone. It is a data record built by a living creature written in chemistry as it tried to survive at the edge of sea and sky. The oceans have currents like rivers driven by heat and salt. The surface of the sea can look still, but enormous flows are always on the move. Warm water tends to expand and stay buoyant, while colder, saltier water becomes denser and sinks. That density contrast helps power a planet spanning circulation that shuttles heat from the tropics toward higher latitudes, then returns colder water at depth. Where winds push surface waters away from a coastline, deep water can rise to replace it, bringing nutrients up from the dark and fueling productive fisheries. Currents also steer storms and shape regional climates because the ocean stores heat far more efficiently than air. Even oxygen levels are influenced by circulation, since mixing helps ventilate deeper layers. If a current strengthens, weakens, or shifts course, coastlines can feel it through changes in fog, rainfall, and sea ice. Ocean currents are Earth's moving climate wiring, and they never stop. Hydrothermal vents build mineral chimneys, growing like underwater factories. At certain spots on the seafloor, cedar seeps into cracks, descends, and heats up near Hawk Rock. It then rises back out, loaded with dissolved metals and minerals. When that hot fluid meets cold cedar, the dissolved material can precipitate instantly, building tall chimneys and flanges that look like dark stone sculptures. Some vents produce billowing plumes rich in metal sulfides, and those particles can settle to form deposits that resemble underwater ore bodies. Chimneys can grow, collapse, and regrow, changing shape in months or years, which is fast in geological terms.
Because the fluids are chemically reactive, they can also alter the surrounding rock, creating distinctive mineral zones that mark where circulation once occurred. These systems are like natural reactors, moving heat and chemicals through the crust and constructing architecture from the ingredients of seawater and stone. Life thrives at vents without sunlight, powered by chemical energy. Some vent animals live in partnership with microbes that turn vent chemicals into usable energy. Giant tube worms are a famous example because they lack a typical digestive system and instead house dense communities of bacteria inside specialized tissues.
Their blood contains unusual molecules that can carry both oxygen and sulfite safely, which lets them feed their microbial partners without poisoning themselves. Other vent residents include clams and mussels that also host internal bacteria, plus shrimp that graze microbial films growing on rocks. Growth can be rapid compared with many deep-sea environments because the chemical fuel can be intense and continuous. Vent fields are also patchy and temporary, which means species must disperse to new sites when an old vent shuts down. The result is a network of biological outposts on the seafloor, connected by drifting larvae and shaped by the rise and fall of the vents themselves. Methane seeps host strange ecosystems fueled by gas from below. In some seafloor regions, methane leaks upward through sediments from deep reservoirs or from methane hydrates locked in cold layers. Where that gas meets seawater chemistry, microbes can consume methane in reactions that often involve sulfate. And those reactions can change the local environment dramatically. Carbonate minerals may precipitate, creating hard crusts and rocky pavements on an otherwise soft seabed. These carbonate patches become habitat, giving places for sponges, corals, and other animals to anchor. Some seep communities include mussels and tube worms that depend on microbial partners. But the environment feels different from hydrothermal vents because seep fluids are often cooler and more diffuse. Methane seeps also play a role in the carbon cycle, since microbial consumption can keep some methane from reaching the water column and the atmosphere. A seep is like a slow leak from Earth's interior pantry, and entire communities can gather around it. Ocean sediments can also hide microplastics, creating a new kind of geological marker. Lastic fragments are now found from beaches to deep-sea mud, and many of the smallest pieces settle into sediments like grains of sand. Over time, layers can accumulate that contain distinctive synthetic polymers mixed with natural materials such as shells and clay. Future geologists may identify these layers by their chemistry, their shapes, and even the additives used during manufacturing. Microplastics can also attract and concentrate pollutants, which may change how chemicals move through seafloor ecosystems. In quiet basins, where sediments accumulate steadily, the record can become surprisingly clear, with microplastics appearing as a signal of recent human activity. Unlike a footprint that washes away, a buried layer can persist and be compacted into future rock. That makes microplastics more than litter. They are potential stratigraphic clues, a durable signature of an industrial era written into the same archive that preserves ash layers and ancient shells. Humans have created new rocks like concrete on a global scale. Concrete is made by binding sand and gravel with cement, and cement is produced by heating limestone and other materials until they react and form new compounds. Once mixed with water, those compounds harden into a stone-like mass that can last for decades or far longer. As cities expand, concrete becomes a widespread layer of human-made geology, filling foundations, roads, sea walls, and bridges. Over time, concrete can crack, weather, and be buried by sediments, creating future layers that contain rebar, glass, brick, and other manufactured fragments. Some researchers describe these materials as technoposals because they are distinctive and datable. Concrete also interacts with the atmosphere, since the chemical process of making cement releases carbon dioxide, while aging concrete can slowly reabsorb sun. Whether you see it as building material or future rock, concrete shows that human activity now shapes the planet's surface in a way that will be readable in the geological record. City heat and surfaces can change local weather, affecting rainfall patterns. A city replaces vegetation with dark roofs, asphalt, and concrete that absorb sunlight and store heat. That warmth can make urban air rise, and rising air can help trigger convection, especially when moisture is available. Cities also add particles to the atmosphere from traffic, industry, and construction. And those particles can influence how clouds form and how droplets grow. The result can be complex. Some cities experience more intense downpours in certain conditions, often downwind, where the rising air and cloud processes have the right ingredients. Lightning frequency can also be affected during storms that pass over warm urban centers. At night, cities cool more slowly than surrounding countryside, which can keep local winds and temperature gradients active for longer. This means weather is not only a product of oceans and mountains, it can also be shaped by the geometry and heat of the built environment. A skyline can subtly steer the sky. Groundwater can be ancient stored since colder climates long ago. Not all groundwater is part of a quick, local cycle. Some aquifers hold water that infiltrated during past climates, when rainfall patterns and temperatures were very different. In arid regions, recharge can be so limited today that the water being pumped is effectively a one-time inheritance from wetter periods. Scientists can estimate ages using dissolved gases and isotopes, which act like timestamps for when the water last contacted the atmosphere. Ancient groundwater can be remarkably pure, filtered through rock for thousands of years, but it can also pick up minerals that make it salty or rich in certain elements. Some aquifers are confined under layers that trap pressure, creating artesian wells that flow without pumping when tapped. The concept is both comforting and unsettling. There can be water beneath a desert that fell as rain when the region had grasslands and lakes. Once used up, it may not return on human timescales. Aquifers can collapse when overpaint, causing land to sink. An aquifer is not an underground lake. It is water stored in the pore spaces of sediments and rocks. When water is withdrawn, pressure drops and the grains compact more tightly together. In soft sediments, that compaction can become permanent, which means the aquifer loses storage capacity even if water later returns. At the surface, the result can be subsidence, a slow sinking that can crack canals, tilt buildings, and increase flood risk. In coastal areas, subsidence can worsen storm surge impacts and make high tides reach farther inland. It can also contribute to saltwater intrusion, since lowering groundwater pressure can allow seawater to move into freshwater zones. Subsidence often happens unevenly, which creates stresses that damage infrastructure in unexpected places. The deeper story is that groundwater is part of a structural system. Remove too much support, and the ground itself can settle, turning a hidden resource problem into a visible landscape change. Some lakes turn over seasonally, mixing oxygen and nutrients in pulses. In many temperate lakes, summer warmth makes the surface water lighter, so it floats on top of colder, denser water below. That layering can trap deep water in darkness, where oxygen slowly gets used up and nutrients can build. When autumn cools the surface, the temperature difference shrinks. Wind can then stir the whole lake, and the water column mixes from top to bottom. This stir can bring oxygen down to depths that have been starved for months. It can also bring nutrients up towards sunlight, which can spark fresh growth of algae and microscopic life. In spring, a similar mixing often happens after ice melts and surface water warms back through the same temperature range. These seasonal pulses shape fish habitat, water clarity, and even the smell of a lake after a windy day. A lake can look calm, but inside it is breathing on a schedule. Acid mine drainage shows how chemistry can turn streams bright orange. When sulfide-rich rocks are exposed during mining, they can react with oxygen and water to form sulfuric acid. That acid can dissolve metals from surrounding rock, carrying them into nearby streams. As the acidic water mixes with cleaner water and meets oxygen, iron can precipitate out as rusty orange coatings that blanket stones and stream beds. The color can look almost unreal, like the water has been painted. The damage is not only aesthetic. Acidity can stress aquatic life, and dissolved metals can be toxic even when the water looks clear. The good news is that this process is also predictable, which makes it possible to monitor and treat. Some cleanup methods add alkaline material to neutralize acid, while constructed wetlands can encourage reactions that remove metals. Acid mine drainage is a lesson in unintended consequences. Digging into earth can change chemistry in ways that travel far beyond the mine itself, reshaping whole watersheds downstream. Natural springs can deposit travertine, building terraces over centuries. Some groundwater dissolves limestone underground and carries the dissolved carbonate to the surface through springs. When the water emerges, it can lose carbon dioxide to the air, and that shift makes calcium carbonate precipitate as solid rock. Layer by layer, the spring lays down travertine. Over time, it can build rimmed pools, stepped terraces, and smooth cascades that look sculpted, even though they're grown by chemistry. The textures can be delicate. Tiny ripples and plant stems can be coated and preserved as stone. Color often comes from trace minerals or from microbial mats that thrive in the flowing water. Travertine landscapes also record change. If a spring shifts its outlet or its flow rate changes, the building pattern changes too, leaving abandoned terraces like older stair steps. These deposits show geology happening on a human scale, slow enough to watch, yet fast enough to reshape a hillside within a lifetime. Geysers need very specific plumbing, and shifting minerals can shut them down. A geyser is not just hot water. It is a carefully balanced system of heat, water supply, and underground passages that can trap pressure. Water seeps down, heats up near hot rock, and becomes superheated under the weight of water above. If the plumbing has narrow constrictions, steam bubbles can collect and build pressure until the system flashes into eruption, blasting water and steam out at the surface. That is why geysers are rare. Most hot springs do not have the right geometry to cycle in this dramatic way. The plumbing is also fragile. Minerals can precipitate from hot water and slowly coat the passages, changing the shape of the tubes.
Small earthquakes can open new cracks or seal old ones. Even shifts in groundwater can alter the timing. A geyser field is a living laboratory. It can gain new vents, lose old ones, and change rhythms without warning. When a geyser goes silent, it is often because the underground plumbing has quietly rewritten itself. Permafrost stores carbon, and thaw can release it back to air. In cold regions, soil can remain frozen for years or even for millennia.
That frozen ground can lock away plant material that never fully decomposed, because microbes work slowly when temperatures stay low. The result is a vast store of carbon held in place by ice. When permafrost thaws, the ground can become waterlogged and unstable. Microbes wake up and begin breaking down that stored organic matter, releasing carbon dioxide in oxygen-rich conditions and methane in waterlogged conditions. Thaw can also change landscapes quickly. Ground can slump, lakes can form, and coastlines can erode faster as ice that once cemented sediments disappears. This matters because it links climate and geology in a feedback loop. Warming can thaw permafrost, and thaw can add greenhouse gases that contribute to further warming. Permafrost is not only frozen dirt, it is a long-term carbon vault, and thaw is the door beginning to open. Volcanic soils can be very fertile, supporting dense forests and farms.
Fresh volcanic ash and lava fragments can weather into soils rich in minerals such as potassium, calcium, and magnesium. Over time, rain and biological activity break the material down into fine particles that can hold water and nutrients. In many volcanic regions, this creates dark soils that can support intense plant growth, which is why some of the world's productive agricultural areas sit near active or recently active volcanoes. The trade-off is risk. The same volcano that provides mineral-rich soil can also deliver ash falls, lars, or lava flows that endanger communities. Volcanic soils can also behave in distinctive ways. Some develop strong structure that resists erosion, while others can be prone to landslides on steep slopes during heavy rain. These landscapes show a striking balance. Volcanism can be destructive in the short term, yet it can also renew the ground that feeds ecosystems for generations.
A volcano can be both a hazard and a source of abundance, depending on the timescale you choose.
Earth's carbon cycle moves through rocks, oceans, air, and life. Carbon is not confined to the atmosphere. It moves through a vast system that includes living organisms, seawater, sediments, and even the mantle. Plants pull carbon dioxide from air, then pass it into soils and food webs. In the ocean, carbon dissolves and can be used by organisms that build shells, which later become sediments and carbonate rocks. On land, weathering can draw carbon dioxide into chemical reactions that eventually send carbonate ions to the sea. Deep underground, subduction can carry carbon-bearing rocks into the mantle, and volcanism can return carbon dioxide back to the air. This is not a simple loop with one speed. Some carbon cycles in days through leaves and microbes. Some stays locked in limestone for millions of years. The carbon cycle links climate to geology,
And it helps explain why Earth can change temperature over long spans. It is a planet-scale accounting system, constantly moving carbon between reservoirs that feel separate, yet are tightly connected. Minerals can record past temperatures, acting as tiny geological thermometers. Certain minerals form in ways that depend on temperature, and their chemistry can preserve that information long after the heat is gone. In metamorphic rocks, minerals can grow in sequence as conditions change, and each mineral has a stability range that acts like a clue. Some crystals even preserve zones with slightly different compositions from core to rim, which can reflect changing conditions during growth. In some settings, pairs of minerals exchange elements between them until they reach a balance that depends on temperature, and that balance can be measured later. This lets geologists estimate how hot rocks once became during mountain building or deep burial. These temperature records can also reveal how quickly rocks moved upward, because rapid uplift can freeze mineral patterns before they fully re-equilibrate. The magic is that stone can remember heat. A hand sample can contain a thermal history that no person ever observed. Yet with careful measurement, it can be reconstructed. Minerals are not just building blocks. They are witnesses, recording temperature in the quiet language of chemistry. Earth science connects everything, from mountains and storms to oceans and life. It's easy to treat landscapes, weather, and ecosystems as separate subjects, but they are threads in the same fabric. Mountain building shapes rainfall by forcing air upward, creating wet, windward forests and dry, rain-shadowed deserts. Rivers then carry eroded sediment to the coasts, forming deltas and nourishing wetlands that protect shorelines. The ocean absorbs heat and releases it through currents, influencing storm paths and seasonal cycles on land. Soil links the living and non-living because it forms from weathered rock but is powered by microbes and roots. Even natural hazards reveal these connections. Earthquakes can trigger landslides that block rivers, and shifting climate can alter snowpack and the timing of floods. Earth science is the study of those connections. It explains why a change in one place can echo elsewhere, sometimes far away and much later. Once you see the links, the planet stops looking like a collection of separate scenes. It starts to look like one interacting system, always responding, always adjusting. Every landscape is a snapshot caught mid-change on a restless planet. A canyon wall may look permanent, but it is a moment in a long process. Rivers keep cutting, slopes keep failing, and rock keeps turning into sediment that will become new rock elsewhere. Coastlines shift as waves rearrange sand, and as land rises or sinks. Forests advance and retreat with climate, and soils thicken or thin depending on how fast rock weathers and how fast erosion removes it. Even the quietest plain can hide motion. Groundwater can dissolve minerals and open cavities, or it can deposit new cement that hardens sediments in place. If you could speed up time, hills would move like slow waves and shorelines would walk across the map. The beauty of earth science is learning to read that motion in the present. A landscape is not a finished product. It is a frame in an unfolding story shaped by processes that never stop, whether we notice them or not. As we come to the end of our journey through earth science, you might notice how the planet feels a little more alive than it did before. Beneath every step, there are layers stacked like history books, and deep engines moving rock with patient force. Coasts shift, valleys widen, mountains rise, and then slowly wear down again. Even the quiet seafloor is busy building fresh crust, carving trenches, and growing mineral towers in the dark. Above it all, air and water keep circulating, carrying heat, salt,
dust, and nutrients across the world, stitching distant places together. And while we've been listening, the Earth has been doing what it always does. Rivers have continued to pull at their banks. Waves have continued to sort grains of sand. The magnetic field has continued to reach outward into space. The planet does not pause, and it does not rush. It changes in its own steady way. Now you can let those ideas soften into the background. Imagine a wide landscape at dusk, the last warmth held in stone, the horizon calm and open. Let your breathing slow. Let your shoulders soften. Let your thoughts drift like clouds that do not need to decide where they are going.
If an image of a glacier, a canyon, or a deep ocean trench returns to you, let it pass through your mind without effort, like a quiet postcard from a vast world. If you enjoyed this slow wander through the science of our planet, you can support the channel by liking, subscribing, or leaving a thought below. And if you're still awake, there will be another video waiting on your screen, ready to carry you onward. For now, rest is enough. Sleep well, and good night.